So mathematicians, well, they exist and some of them do research, but what exactly is it that mathematicians do? So the Journal for the American Mathematical Society is one of the most well-respected and well-known math journals in the world. So I looked at their last 10 publications, and this title was officially the easiest for me to understand. Sharp isoparametric inequalities for affine core-mass integrals. Whoa. So to unpack this title a little bit, core-mass integrals are a type of mixed volume, which is a way to characterize the orientations and sizes of multiple shapes with one number. And this article in particular shows that out of all the objects in any number of dimensions, shapes like these, ellipsoids, have the smallest core-mass integrals. And do any of you have any idea of what I'm talking about right now? Yeah, it's not just you. Modern math is so specialized that even other mathematicians in a field that's not mixed volume would struggle to understand anything that's going on in this paper. So then, if even other mathematicians can't really understand these results, how can we expect physicists, chemists, and engineers to utilize these results in the real world? Well, the short answer is that we can't, not really. Most mathematicians today agree that the majority of published math results aren't really useful in the real world. They don't really have a real world application. So then, why is someone spending thousands of hours writing 43 pages about core mass integrals? And why should society fund math research at all? Admittedly, most of the math we encounter in our lives is immediately useful. Our modern society runs on algebra and calculus and Fourier transforms. Undergraduate students in math will study group theory, which is the theory of how things can be symmetrical, and this is the foundation of modern physics and chemistry. But past the graduate level, the connection between math and the real world becomes increasingly unclear. The famous British mathematician G.H. Hardy once said that we have concluded that the trivial mathematics is, on the whole, useful, and the real mathematics, on the whole, is not. But this doesn't mean that we shouldn't continue to explore math. For one thing, things in math tend to come back around. I've heard it said that the physics of today is built upon the groundwork laid out by mathematicians 50 or 100 years ago. For example, mathematicians have studied non-Euclidean geometry, which is the geometry on top of curved surfaces, like in that second and third image there, for centuries. And for the most part, people thought this stuff was kind of cool, but also useless, because why would you ever need geometry that's warped and curved? But then in 1916 or so, this guy that you might have heard of, called Albert Einstein, he came along and showed that the space-time we live in is actually curved by massive objects. So to accurately describe the universe around us, we need to use non-Euclidean geometry. And this stuff is important. Without accounting for the curvature of space-time, without accounting for relativistic effects, GPS satellites would be off by 5 miles every day. And that would make this pretty useless. Another example of math that people thought was useless, that turned out to be pretty useful, is prime numbers. 400 years ago, Euclid and Fermat developed their prime number theorems at a time when they thought they were just playing around and finding out pretty theorems about numbers. But today, this is the foundation of modern cryptography, and you can bet that banks and governments are relying heavily on the theorems developed by Euclid and Fermat 400 years ago. But this isn't really the full story, because mathematicians today aren't studying math because they think in 50 or 100 years some computer scientist is going to come along and make some revolutionary new technology out of the math they're developing today. Instead, to most mathematicians, exploring math is kind of like following a path or writing a story. It's part of human nature to naturally want to seek out answers and to explore about the universe we live in. To study math is to try to answer at the universe's most fundamental level why the world is as it is. And this desire to explore, this is what made George Boole develop Boolean algebra, which is the algebra of ones and zeros, 100 years before the first computer was ever built. And it's why the ancient Greek mathematicians explored conic sections, which, to my knowledge, had no applications in the real world until 2,000 years later, when Johannes Kepler discovered that planetary bodies follow these conic paths. Now, this desire to explore and to seek out new lands isn't something that's limited to the top mathematicians. No, this is something that everyone has. And to find something that you're really curious about, something that makes you think in a new way, or something that you can be creative with, no matter whether you think it's going to be useful or not, will open up opportunities for new growth. Thank you.